Newton's first law, then we have the second law and third law of motion. So I'm going to explain to you what each of these laws are. I'm going to briefly tell you what they represent and how those laws affect our day-to-day lives. All right. So every object continues in its state of rest or of uniform motion or uniform velocity in a straight line as long as no net force acts on it. So what that simply means is that if you are at rest, if you're not doing anything, you're going to remain in that state, except there is an external force that comes to act on you. All right. If you, a particle, an object, or anybody whatsoever is already in motion, you will continue in that motion. That object will continue in that motion, except there is an external force that comes, to act on that particular body or you or that object or particle in motion. This is very, very important. Also, when we are dealing with a frictionless smooth surface, you should know that it simply means that when an object is moved forward, that means there is no force of friction acting on that particular object. The force of friction is a force that acts in opposition to the force that is moving a particular body in a particular direction. So if there's a force moving the particle in the forward direction, the force of friction will be in the backward direction. But what we are dealing with at the moment is a frictionless smooth surface. So if you have a frictionless smooth surface, it simply means that there is no friction acting on the particle moving forward. Okay, so the movement is easier; it goes forward straight away. All right. Also, you should know that the summation of all forces acting on a particular body are expected to be zero. And as you know, force is a vector quantity. Okay, so all the forces acting on a particular body in whatever direction, the summation of all of those forces put together should be equal to zero. Okay, so also I want to quickly point out that the acceleration of a body is always in the direction of the force acting on the body. The acceleration on the body is always in the direction of the force acting on the body. So these are important information that you have to pay attention to. And this particular slide gives you some other details that I think would go a long way to solidify your understanding on this particular discussion and topic. Okay. What is the relationship between force and mass? What is the relationship between force and mass? When you hear the term standard mass, the standard mass is usually represented with 1 kilogram. Okay, so it means when you exert a force of 1 Newton on a standard mass, which is 1 kilogram by the way, that particular particle will experience an acceleration of 1 meter per second squared. Because we do know that our force is always equal to the product of mass and its acceleration. And like we mentioned earlier, force is a vector. If force is a vector, our acceleration would also be a vector. And I also mentioned earlier, let me say it again, that our acceleration is always in the direction of the force. So as you can see here, you can see the force here. This force is in the forward direction, so the acceleration here would also be in that direction. As you can see, this is a frictionless table. We have a particle on the table. You can see the force. So let's say the force is pulling this particular particle forward. The acceleration will also be in that exact direction of the force that we have. Let's talk about the mass briefly. If the same force acts on two different bodies, let's say we have two bodies, and then the same force is acting on the two bodies. That simply means the force on body A, let's say the body A or body O has MO as its mass, AO as its acceleration, then body X has MX as its mass, and then AX as its acceleration. So if both of them are experiencing the same force, it simply means F would be equal to MOAO. That same F would be equal to MXAX. So if we have, from our general knowledge of mathematics, if we have this kind of an expression, it simply means we can say that our MOAO equal to MXAX. Rearranging this expression alone can give us mx over m naught or mo equal to a naught over ax. This is a very, very important expression for you guys. It gives you an idea, how an idea on how you can treat masses of bodies or particles that are experiencing the same force on them. basically. Okay, so if you would define mass, the mass of a body, it will be defined as the characteristic that relates the force on the body to the resulting acceleration. Let's take it a step further. Newton's second law. What does Newton's second law say? It says that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. The acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. Okay, so when you put all of those together, it simply means that your force is going to be equal to mass times acceleration. Okay, if acceleration is directly proportional to force and inverse proportional to mass, it simply means that F will be equal to ma. So the summation of all the forces will be equal to mass multiplied by acceleration. And like we mentioned some time ago in the classroom, we said that whenever we have force, whenever we have a particle or a body moving or that is experiencing motion, there are possibilities of having two-dimensional motions and there are possibilities of having three-dimensional motion. All right, so if we have different dimensions of motion on a particular object, it simply means that we can find the force acting on that particle in different dimensions that we have. So the first expression you see here as summation of f of x, what does this represent? It represents horizontal force acting on the particle. So what you will find out here is that the mass is constant here, there is mass here, but what changes is the acceleration. So what you will see here is ax, which represents the horizontal acceleration. Summation f of y represents the vertical force. What you will see here is, in this case, we are not going to use ax because we should have our ay, which is the vertical acceleration. So we use that to find the vertical force. The same will go with fz, force in z direction. You can use the az to find the force in z direction. And these are some units that you should be able to play with. We have the SI unit, we have the CGS unit, we have the British unit. For the sake of our classroom, we'll be focusing on the SI unit. At some point, we'll mix them up with the CGS unit, but then you should know that our duty is to try to convert any other units given to us to the SI unit before we start our calculations, or we do the conversion after we have completed the calculations. But whatever you do, if you're using the CGS unit, make sure that you have all of these units in the way they are before you use them and carry out your conversions. If we go further, let's just briefly talk about weight. Okay, let's talk about it. Weight of a body is a force that pulls it directly towards a nearby astronomical body. So a gravitational attraction between the masses of two bodies, is what we refer to as weight. Okay, so you are a body, the earth is a body. Okay, so if there's going to be an attraction between you and the earth, all right, so that gravitational pull between you and the earth is what we refer to as weight. Okay, so a body mass is located at a point where the free fall acceleration is g. We already know that. Okay, so this is just important. If you go through these particular explanations, the information details there, you will get other details that will strengthen your knowledge about weight. And when we are discussing weight, you have to pay attention to the inertial frame. Okay, so your weight when you're on Earth will be different from your weight when you are in the moon. Your weight when you are on Earth will be different from your weight when you are in a different inertial frame entirely. Okay, so pay attention to that. That is also very, very important. Okay, so now let's talk about the normal force, the frictional force, and then the tension. What you will see here, as you can see here, we have the normal force. The normal force is represented with N, and then W is the weight. What you will see here is that the normal force and the weight are in opposite direction, directly in opposite direction, and both of them are perpendicular to the horizontal. Okay, the normal force is perpendicular to the horizontal and it is an upward force. The weight is perpendicular to the horizontal and it is a downward force. Can you see that? So it simply means that the summation of these two forces is expected to be equal to zero. That is what it simply means. The summation of these two weights, taking account the direction of movement, is going to be equal to zero. All right. So this is very, very important. Pay attention to it. Also here you can see the second figure we have here. You can see friction. It explains friction, and then you can see a particle move in a particular direction. You can see the force moving that particle in the forward direction. So this is the direction of the force. It is sliding forward, but you will see that there is another direction sliding backward. this direction going backward is what we refer to as the frictional force. I mentioned earlier that the frictional force is always an opposing force to the force acting on a particular body. So as this force F, the capital F is trying to move the body forward, the small f, which is the frictional force, the small f, which is the frictional force, is trying to pull the body backward or prevent the body from sliding forward. This is very important. And then the tension is the force in the core. Okay, so the normal force is a force, the weight is a force, the frictional force is also a force, the tension is also a force. So this tension is always the force that is always the force in the core. If there is a core that is being used to pull a particular body, in the case of, let's say we have a pulley. Okay, so if there is a force that is trying to pull the body and we are pulling that body with a particular cord, there will always be a force in that particular cord that we are using to either push or pull the body in the particulars. Okay, so pulling that particular body will create some kind of tension in the cord or the rope in which we are using to pull the body. As you can see here, we have a pulley. You can see here there is a mass here. There is a cord attached to the mass, and then here is a pulley, as you can see here, and then there is someone trying to pull this pulley. So the cord that is being used to pull the pulley in this particular direction, you will find out that this particular cord will have some force inherent in it. Will have some force in it, and that force is what we refer to as tension. Okay, so this is a pulley, or a case where we have a body on the table, okay, or on a flat surface, and then we have a pulley connected at an hinge here. You can also pull this particle or this body, this object, across this particular pulley using a cord. So as you try to pull, you will see here that there is a tension here in this particular cord. Okay, as the pulley is going over this, as the body is going over this pulley, there is got a tension in this particular cord, and then as you pull the body down here, there is also a tension in this particular cord. What you will find out here is that this tension here is horizontal, all right, and this tension here is vertical. So when you are finding this particular tension here, you're going to make use of the horizontal acceleration. This is very important. Okay, when you're finding the tension here, you're going to make use of the vertical acceleration. In any case, the horizontal acceleration is always equal to the vertical acceleration. One way or another, you will be able to find the tensions in the cord depending on problems that you're dealing with over time. This is also key. This is very important. So let me see if there's anything here I need to explain again before we go on. So the cord is unstretchable and helps to transfer the tension in different directions. Okay, so you should note that too. In this particular case, the cord is massless and we run around a massless, frictionless pulley. So if it's not a frictionless pulley, it will be mentioned in your exam or in your questions or in any problem or project that you're dealing with. It will certainly be mentioned if it's not a massless, frictionless pulley. But in many cases, we'll be dealing with massless, frictionless pulleys. Okay.